not be hard-coded in it. As the velocity increases, the drag force increases, and that would be opposing the force gravity. And that ultimately would lead us into the terminal velocity, which would be the maximum velocity that object can reach. So, my observations, let's see, you can see that the sponge seems to be moving with a increasing velocity. It doesn't seem to be constant. It's definitely moving with an increasing velocity. But we can't actually say that until we actually have the data. So we're going to use tracker to show that the velocity is increasing. There are several ways you can use the data to show that the velocity is increasing, but we are going to be using a modification of Newton's second law to figure out how the velocity is increasing. And we will be doing this by using the modification that includes velocity, which is the velocity final equals the initial velocity plus the net force divided by the mass times the change in time. So we're going to use tracker to figure out the velocity experimentally first. As we can see in this tracker video, the velocity, this is the position versus time graph. And again, it is going in the negative x direction or negative y direction. So it is decreasing. As you can see, the velocity is decreasing. The position is decreasing in a parabolic way. But that would mean that the velocity would be decreasing or increasing quickly. The velocity would be increasing in a linear direction, which means that there would be an acceleration of the object, which would be a net force. So for my computation in Python, I use the initial velocity, the time, and the mass of the ball, along with the final time the motion occurred. And as the code runs, it's going to factor these variables into Newton's second law, and it's going to iteratively update the new positions and velocities. So I'm going to compare my observations to a model without drag and a model with drag force included. And drag force in this case is turbulent drag, which is a drag force that's more realistic as it includes the rotational forces or the rotational air currents that occur as the object falls. So as you can see, this is my experimental versus computational comparison. The experiment is in blue, the model without drag is in yellow, and the model with drag force included is in red. They are pretty much the same as time is small. As time increases, the model with drag and the experimental model converge, while the model without drag keeps on going lower and lower. And if time increased infinitely, you would see that this velocity would increase infinitely as well. So there are some interesting trends in the data. The observational model shows a position that changes slope slower than the other two graphs, and the model that includes drag is much closer to the true observational graph. And a reason for this deviance would be that the position of the object in the video, you cannot actually see the object hit the ground during that time interval. And that might affect the data to show that there is a slower acceleration than what was computationally found. So, finally, there is one consideration to take into account: the thrown versus dropped time. If the object was thrown downward instead of dropped, the terminal velocity actually would stay the same. If there was enough time for us to actually see the object falling, we could actually see that the terminal velocities would be the same, because the mass actually does not factor into it. The initial velocity does not factor into it. It just matters about the actual object, and the drag force that's occurring on it. So this is lab number 2, the falling future.